And what if your data is multimodal? So what that means is, let's say you have the x-axis, and on this axis you have a bunch of points that are bunched up here, and then it has become sparse, and then again we get another set of dense points. So the distribution here looks like it has some peak here, then it goes down, and then it has another peak here. So there is a very useful density function. It is still parametric, which is called mixture of Gaussians. So basically what it does is that it basically models the data as sum of multiple weighted Gaussians. So there is one Gaussian here, and then there is another Gaussian here, and basically we sum up the two Gaussians. So basically your probability of X is being modeled as sum over some set of Gaussians, and let's say there are k Gaussians, k is equal to 1 to capital K. Okay, and within each we have a weight alpha k. So some of these can be higher, some of these can be lower, but each of them individually integrates to 1, and totally they should all integrate to 1. So alpha k, and then we have normal distribution of xi. Okay, so let's say this is xi, okay, given the mu k and let's say the sigma or ck. Okay. And the constraint is that all alpha k is greater than equal to 0, and sum over k of alpha k is equal to 1. So because each Gaussian itself integrates to 1, their sum should also integrate to 1. Only then this is a probability density function. And for their sums to integrate to 1, we need the weight to be weights to be non-negative, and we need them to add up to 1. So what is this k? This k is basically a hyperparameter, and the mu k, the ck, and the alpha k are the parameters which we will call theta. Okay, so this is the underlying assumption. Here it is not so straightforward to find what are the different alpha k's. It's not easy to find what are the different mu k's and what are the different ck's. So those have to be found using an algorithm which is not as straightforward as taking the sample mean or the sample covariance that we saw in the case of a single Gaussian. Now we have a mixture of Gaussians. So the algorithm that is used here is something called expectation maximization algorithm, and the way it works is the following. So we assume that there is some sort of a membership of each sample point to each of the Gaussians. So that membership is WIK. Okay, and that membership adds up to 1. So if it is relatively more explained by one Gaussian, the weight will be larger. If it is towards the tail end of the second Gaussian, it will be the weight for the second Gaussian will be smaller, but they will all add up to 1. So the way they add up to 1 is that we will take in the numerator we will take alpha k. Okay, so this is your WIK. So what is WIK? The weight or the membership of the ith data point to the kth Gaussian. So this is going to be alpha k, and then we will take the Gaussian probability P of xik. What is P of xik? It is basically the normal distribution of xi given mu k and sigma k. Okay, but now this will be divided by all such terms. So in the new denominator you will have, instead of j I will take instead of k I will take j, but it is basically the same variable. So and now we will have alpha j, okay, pj xi, okay, and j runs from 1 to capital K. Okay, so this is the weight, and the weight for each sample adds up to 1. So so basically we will iterate over a few iterations, and we will stop when there is not sufficient change in, let's say, WIK. So let's see that there are parallels to k-means algorithm in some sense. So basically what we will do, or fuzzy c-means for example. So in the E step, we will compute the memberships, and in the M step, in the maximization step, we will maximize the likelihood of the data given the weights. So we will keep the weights fixed, but we will find the maximum likelihood estimate of theta keeping the weights fixed. So what that means, that alpha will be the fuzzy membership divided by the total number of samples. So what is nk? Nk is sum of all the weights of all the samples for this particular k, and we will do this for all k. This will be for k is equal to 1 to k. Then the maximizing the mu that maximizes the likelihood is the weighted average of all the points weighted by the membership to that particular Gaussian. Okay. And then the ck for each class each Gaussian is going to be the average over all these points, but of the covariance. So it's going to be xi minus mu k and xi minus mu k transpose, but then it will be again weighted by wik. Okay, so this, if we iterate over this, we will be able to find the alphas and the mu's and the ck's for the mixture of Gaussians. Now let's go back a bit to the model and let's see the parallels between mixture of Gaussian models and k-means and fuzzy c-means. So here what you can see is that the number of samples that are in one particular k-means or fuzzy c-means cluster, those are represented by alpha k. So that is basically the weight of that particular cluster. In this particular case, it's the weight of that particular Gaussian. And then their centroid is mu k, and in fuzzy c-means and k-means, we assume that the covariance matrix is a scalar multiple of identity matrix. The data is isotropically distributed, and we also assume that all the covariance matrices are equal. Here we don't assume that. Here all the Gaussians are allowed to have different covariance matrices and skewed not skewed, but covariance matrices that are not axis aligned. They can be tilted, for example. But then when we look at the estimation, the learning algorithm for k-means and EM algorithm, there are parallels here. The parallel here is, for example, here we have in k-means we would have measured the cluster membership, and then we would have simply updated the centroids of the clusters. So similarly here we are measuring the fuzzy membership in some sense to each Gaussian based on how likely it is to belong to that Gaussian relative to other Gaussians, other of the k Gaussians, not like any Gaussian, other of the k Gaussians in the mixture. And then we are looking at what is the maximum likelihood estimate of the mu and the sigma for each Gaussian, and for the alpha of each Gaussian, or the weight of each Gaussian. So think about it this way. Let's say we have a bunch of points, and this is a multimodal Gaussian distribution, right? So this looks like it comes from two different modes. So we can randomly initialize some mu k here, some mu k here, and some sigma k here, and some sigma k here, not sigma k, ck. Okay. And we can say that here alpha is equal to half, here alpha is equal to half. Okay, so both are equally likely. Now what we can see is that these points are more likely with respect to this Gaussian. These points are more likely with respect to this Gaussian. These are less likely with respect to the other Gaussian, and these are less likely with respect to the other Gaussian. So wherever you see dotted lines, the weights will be smaller. Where you see solid lines, the weights will be relatively larger. So once we do that, when we compute the mu k, the contribution of the larger weights will be more. So hopefully in the next iteration, the mu1 will shift here and the mu2 will shift here, and the relative contribution, the relative number of points in the vicinity will also change the alpha k. So the alpha of this will become larger because it is explaining more points, the alpha of this will become smaller because it is explaining fewer points, and the ck, or the covariance matrix will also tilt. Okay, it will have the required skews to explain based on what is the covariance of this particular sub Gaussian, or the Gaussian in the mixture, and this particular Gaussian in the mixture. So the eigenvalues and the eigenvectors will adjust to explain those, and within a few iterations we'll have basically this kind of the final distribution will be something like a multimodal distribution.